So just a little review from yesterday. I asked you to put these three equations in slope-intercept form and in standard form if they're not already in standard form. So first, let's look at this top one. This negative 3 equals x plus y. Well, this is already in standard form because you've got the x and the y on the same side of the equal sign. So to put it in slope-intercept form, I know that I want y to be all by itself. So that's our goal, is to get this y here all by itself. So that means I need to take this x term and move it to the other side of the equal sign. In order to do that, I've got to get rid of it from this side. So if it's a positive x, to get rid of it, I subtract x from both sides. So if I subtract x from this side, I must also subtract x from this side of the equal sign. Remember our little imaginary line that goes down through the equal sign here. So it's going from here. X take away x, we know, is just 0. And we know that now we have negative 3 on this side. Oops, my pen's writing in white all of a sudden. Okay, so negative 3 minus the x equals y is what I'm left with. This is kind of in slope-intercept form, but I like for you to have the x term first. So we've got negative x minus 3. I just reordered them. I kept the sign that was in front of it, so I moved the negative x to the front, then the minus 3 equals y. And now it is in slope-intercept form. So we have x plus y equals 3. That's our standard form. And negative x minus 3 equals y is in slope-intercept form. Now remember, I told you if you're graphing it, you want the equation to be in slope-intercept form because you know the slope, you know the y-intercept. So that's going to allow you to graph the intercept first, and then the slope allows you to find the next point. Okay, so this equation, this next one over here, it is already in standard form as well. We've got the x and the y together on one side of the equal sign, and then the constant term over here by itself on the other side. So that's great. Now we want to put it in slope-intercept form. So I want to take this positive 2x, and I want to move it to the other side of the equal sign. Well, I know in order to do that, I've got to get rid of it from this side. It's a positive 2x, so I subtract 2x. Whatever I do to one side of the equal sign, I must do to the other, because it's like having a set of scales. I want to keep it balanced. So 2x, take away 2x, that's gone. I'm left with 3y equals a negative 2x is left on this side, and a positive 4 is left on this side. I'm almost there, but I want y all by itself, so I've got to get rid of this 3 that's being times by y. I'm not moving the whole y term over, so I'm not adding or subtracting. I'm just separating the 3 from the y, so I divide every term by 3. So I have y equals negative 2/3 x plus 4/3. So if I wanted to graph this, I would start off by graphing 4/3 along the y-axis. Then I know I would go down 2 and to the right 3, or up 2 and to the left 3, so that I have a negative slope of 2/3. Okay, now this equation is not in slope-intercept form or in standard form. I could very easily get it in standard form if I just move this 2x over to the other side. So I know I want to have to subtract. So negative 2x plus 6y equals 4. Now look at what all of these terms are divisible by. I've got a 2, I've got a 6, I've got a 4. Every last one of these is divisible by 2, or we would say the greatest common factor of each of these terms would be 2. So I'm just going to simplify it and divide everything by 2. So negative 2 divided by 2 would just be a negative 1, or we would write it as negative x. 6 divided by 2 is a 3, 3y. 4 divided by 2 is 2. So I have the equation. Okay, now I want to put it in slope-intercept form. So I can either use this equation that I have here, or I can go back and start with the other one. It doesn't really matter. Let's see here. Let's just start with this top one up here, just in case I made some sort of mistake somewhere along the way. So I'm going to have 6y equals 2x plus 4. That's almost in standard form, or I'm sorry, slope-intercept form. I just got to get the y by itself. So if I divide everything by 6, I end up with y equals 2 over 6. 2 over 6 just reduces to 1/3 x. 4 over 6 reduces to 2/3. So plus 2/3. Now it's in slope-intercept form. So standard form, slope-intercept form. Up here we've got standard form, or I'm sorry, that was slope-intercept form, standard form. Let's see, here it's already in standard form, and then here I converted it to slope-intercept form. So hopefully that makes sense. And we will. So what we want to look at today is functions. A function is just a relation in which each member of the domain is paired with exactly one member of the range. We talked about before, the domain is just a list of all of the x values from a set of ordered pairs, and the range is the list of all the y values from a group of ordered pairs. Now what we want to do is determine whether this relation or this group of ordered pairs is a function or is not a function. And once again it says that each member of the domain is paired with exactly one member of the range. So if you look at my little mapping that I have drawn here, the 1 and 2, 1 is paired with -1, 2 is paired with 0. So each member of the domain, that's my x values, which is right here, each x value is paired with only one y value. So this would be a function. But if you look at this one, you've got the domain of 1 that's paired with not exactly one member of the range, but 2 members of the range. So this is not a function. Okay, let's move on. If you're wanting to determine if it's a function or not, the first thing I always look at is the x values. If there are 2 x values the same, then we've got an issue. If there are no 2 x values the same, then no problem. Move on. We know it's probably a function. But if you look at the x values and there are 2 that are the exact same, then next you have to go on to the second step and look at the numbers that are the corresponding y values. If those are the same, then we're okay. But if they're different, then we've got a problem. So we're going to look at all the values for x and all the values of y for this given relation. So we've got 5, 2, 3, 5, -2, 3, and -5, 1. So first let's look at the x values. Are there any x values that are different? I've got 5, 3, -2, -5. They are all different. So since the domain is all the x values are different, then I know that they are paired with only one element in the range. So this relation is in fact a function. Okay, let's look at a graph of one. Let's look at my x values. I've got x at -3, x at -2, and x at 1, and x at 2, and x at 3, and 2 different x's here at 4. And if you think about it, it's pretty easy to tell by looking at the graph. This x is clearly paired with a different y than this x is. So it doesn't meet our criteria that each element of the domain is paired with exactly one element of the range. So this is not a function. There are points at 4, 4, and 4, -3. So the x value of 4 is paired with 2 different y values, which we discussed. That was 4 and negative 3. Therefore, it cannot be a function. If you notice, oops, that's not what I meant to do. If I was going to draw a line through these points, it only passes through this point here once. It only passes through here once. But look what happens over here. The vertical line's passing through 2 different points, which brings me to my next definition. It says if any vertical line passes through no more than 1 point, the relation is a function. So sliding this line along here. If it only passes through 1 point at a time, then it passes the vertical line test. Therefore, it is a function. So this relation here is a function. Okay, if I look at this one, I could slide this line along through here. Is this going to pass the vertical line test? Yes, because no matter where I slide this line, it's only passing through 1 point at a time. Therefore, this relation is a function, and I hope you guys know that this is an absolute value function because the graph is a V shape. Okay, if I look at this one, this is a parabola. Probably many of you remember this from Friday's lesson. It's called a parabola, and it does not pass the vertical line test. Therefore, this parabola is not a function. Okay, I can tell by looking, this is a straight line. If I had a vertical line running through here, it would pass the vertical line test. Therefore, this is a function. Is a vertical line a function? Let's see here. If I take this line and line it up, is it only passing through 1 point at a time? No, it's passing through multiple points. Therefore, this is not a function. Okay, equations that are functions can be written in a form called functional notation. That's what this f of x means. This is functional notation. It's just a fancy way of writing the letter y. And it's to represent function notation. The y and the f of x have basically the exact same meaning. What this tells me, if I have, we had f of x equals x minus 4. So here I have f of 2. I want to know what is f of 2. Well, if you notice, I replaced the x with a 2. So that's exactly what I want to do on this side of the equal sign, is replace the x with 2. So let's try that here. We got f of 2 equals, instead of having x, I now have 2 minus 4. So we know that f of 2 equals a negative 2. F of 1/2. Instead of having the f of x, I now have f of 1/2. So I've got to replace my x with 1/2. So this equals 1/2 minus 4, which is a negative 3 and 1/2. Okay, f of c. All I did was replace, or all I need to do is replace my x with a c. So I have c minus 4. Okay. If g of x equals 3x minus 7, find g of negative 2, find g of 1.5, and find g of 2h. So I'm just going to line it up directly below it. So I've got g of negative 2. It's going to be a little bit harder than I thought to line it up because my writing's bigger. So I've got 3. Now in place of my x, I want to plug in negative 2, but I keep everything else the same. So 3 times negative 2, we know is negative 6. Negative 6 take away 7 is negative 13. So g of negative 2 is negative 13. Let's find g of 1.5. Okay, I just need to replace my x with 1.5, so I have 3. And in place of x, 1.5 minus 7. 0.5 because you have 1.5 3 times. So yeah, it makes sense that it would be 4.5. Then minus the 7. So 4.5 minus 7 gives me negative 2.5. Okay, let's plug in the g of 2h. G of 2h. So instead of x, I now am plugging in a 2h, but everything else remains the same. 3 times 2h is 6h. 6h minus 7. I can't simplify it any further because this term has an h, this term doesn't. So that is my final answer, 6h minus 7. Okay, let's look at the next one. That might be it. That is it. So that is all I have for you for today. Hopefully you'll be able to determine whether a relation is a function or not. If nothing else, plot the points if you're not sure and see if it passes the vertical line test. And then last of all, finding function values. That's what we were doing here using function notation. You just replace the x with whatever number is here in the parentheses. In place of the x, you replace that x with that on the other side of the equal sign and solve.